Assalamu alaikum warahmatullah. Hello guys, today we will talk about machine learning basics, chapter 5. Let's get started. Okay, my screen, let's get started. Chapter 5. Chapter 5 is very huge and there are many basic concepts we should understand in machine learning. So this chapter will be divided into several videos. Today we will talk about definition of the learning algorithm. What does the learning means? And we will cover one example with linear regression, how machine learning basics applied into this regression problem. So first of all, learning algorithms. So what is learning? What is learning algorithm, machine learning means? And the Mitchell in 1997 in their paper they give very good definition to the learning algorithm. So they are saying that a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. So I am repeating again because if you get this definition right, then it means you can interpret all current models, how this kind of learning models, AI models work. So a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if it is performance at tasks in T as measured by P improves with experience E. Okay. So there are three things to care here. What is experience E? What is task T? And what is performance P stands for? So let me to explain these three things, and we will apply these three things into the linear regression problem. First, it is task. Machine learning generally is divided into three sections, but there is no obvious wall between these concepts. There is no exactly wall between these concepts. They are interconnected actually, but we prefer to separate these things as supervised learning, unsupervised learning, and reinforcement learning. And tasks T are different. For supervised learning, common tasks are classification task, regression task. For unsupervised, it is clustering, anomaly detection, and etc. So here we talk also about, the authors of the book talks about classification with missing inputs, about regression task, about transcription, about machine translation, about structured output, about anomaly detection, synthesis and sampling, and more. So generally, if you have a problem and you can represent that problem as a task, and if that task cannot be programmed, cannot be achieved with traditional programming, then it is time to think about implementing machine learning, thinking to that problem from machine learning point of view. For example, you have a problem of you have a problem that your system should classify between dogs and cats, assuming how you will write in traditional programming that it will understand what is dog and what is cat. This traditional one. So like in programming, how you will represent these pixels, images of the dog, images of the cat, as some kind of object or some kind of thing that your algorithm will understand it. So it is very difficult. So in that case, you should look for machine learning task, for machine learning thing. So here, cats and dogs, we should classify input image, whether it is dog, whether or it is cat. So it's classification task, and we have a task, right? So if we imply this kind of machine learning techniques into that problem of classifying cats and dogs, we can achieve that, so we can have that solution. So it's all about problem, all about tasks. And author of this book are saying that there are many different problems, there are many different tasks. And this list is not limited. This is just common tasks. You can create your own task, or there may be like different tasks. And after saying that, don't focus on this task, and don't forget that this thing is like, these tasks are not limited. Okay, we covered task. Now we should cover what is P stands for, performance. So you have a computer system, it does a task, and you should measure how it is doing good that task. For example, if your program is saying that all images as a cat, not a dog, then it means that performance is somehow bad, wrong. And you should have that kind of metric which will measure the performance of your model. So here, the performance P comes. So for classification, we use accuracy metric as a performance measurement. For regression, we usually use mean square error or mean absolute error, and there are many different kind of measurement metrics, and it is very important to choose right measurement metrics. For example, if your model is doing one task and you are measuring not that actually the task, if you are not measuring the performance at that task, but you are measuring some kind of wrong thing in that performance, then your model will not improve. So choosing the right measurement is important here. So I am again repeating that we talk about task. So there are many different kind of tasks. Most common tasks are regression classification task, because we cannot represent that tasks as a traditional software orientated as calculations. And second thing, performance. If computer system does some kind of task, we need to measure the performance at that task of the computer, whether it is doing good or not. So accuracy is a proportion of correctly predicted labels to total number of predictions. We can associate accuracy as an error rate. So opposite of accuracy is error rate. And I talk about mean square error, so it is about regression. So I will explain it later. Next thing, experience. So what is experience? For example, my father has maybe more than 20 years of experience in medical field. So it means experience, it comes with year, right? We say usually like that. In terms of machine learning, can we say that dataset is experience? Yes, we can say that. In terms of supervised learning, unsupervised learning, if machine learning model uses a dataset means data examples which are real or not real, but they are experience. You have a dataset. And one very good dataset is that Iris dataset. It is one of the oldest one and one of the most popular one for learning machine learning basics. So here, this dataset is a collection of measurements of different parts of 150 iris plants. So it means that there are 150 rows and there are many kind of different measurements. Measurement means not our performance, okay? Like it just makes like what's plant's height, width, some kind of other metrics of the plant, and they are giving the label. So if plant is 2 centimeter height and 1 centimeter has a width, it means it belongs to one class. It belongs to one class of plants. Or if the height is this much, like 10 centimeters, then it belongs to another class. So we have that kind of raw data set, data points, and they are 150. And can we say that this is experience? Yes, that is indeed experience. In this data set, there are 3 different kind of species, flowers. And basically, based on these variables in dataset, model takes that variables and it predicts whether it belongs to one of these 3 classes. So that's experience E, basically. Dataset associated with experience. So unsupervised learning algorithms experience a dataset containing many features, then learn useful properties of the structure of this dataset. In unsupervised learning, it's a little bit different scenario. For example, in that dataset, it is also experience, but the dataset is not structured. It is a bunch of many data samples, and your model should learn something from that dataset. Find some kind of anomalies in that dataset or cluster this kind of datasets. One example may be, imagine you have a lot of files of music in your computer. For example, assume you have 1000 of audio files, and you want to classify or cluster these kind of files into such groups that they belongs to one genre of the music, like jazz, pop music, or maybe K-pop specifically, or maybe old music, country music. So in that case, this your collection of music things, music samples, files, is an experience. And in unsupervised learning, your model should cluster, so separate all these files into some groups that they may belong to. So that's all about unsupervised learning. In supervised learning, it is label, target. So label or target is that in classification problem, we can say label or target is a cat or dog. In our case, for example, if your machine learning model should predict whether this image contains a cat or dog, in that case, label or target is indeed the class name cat or dog. That's all. We talk about experience, about performance, we talk about task. So now example. So it's saying that like you have to read this paragraph, this section. They're saying that the definition of machine learning algorithm as algorithm that is capable of improving a computer program's performance at some task via experience is somewhat abstract. So now we will, now let's see the example in linear regression. So linear regression is algorithm, very simple algorithm, and it is predicting continuous numbers, which means it is a regression task. It predicts continuous numbers, and yeah, it predicts continuous numbers, and it is a regression task. So let's define the three things here. What is task? Here is regression task. What is experience? What is performance? Here in linear regression, there are different performance: mean square error, mean absolute error, or RST, or RMSE, and other bunch of many different measurements. But I select, or generally we select MSE. Okay, we have task, we have performance, we need experience. So if we say that experience is a data set, training data set, that it means if we have that training data set, then we are good to go to train a model. So here they are saying that the output of linear regression is a linear function of the input. So this notation, y with small hat, some kind of like this hat, is prediction of model. So prediction of model is linear, is just the calculation dot product of weight to the input x, input variable. Here x is input vector, and this w stands for weight or parameters. So I think you have heard that maybe like ChatGPT has 7 billion parameters, or something like that, or it has 3 billion parameters. So parameters are the values that control the behavior of the system. In our case, it means that for each value in this vector, we will multiply corresponding element in the vector w. So here, if w is 0, it means it has no impact on the x, or it doesn't have any impact on the prediction. If this w is plus some kind of big number, it means it has positive big impact. If it has some kind of negative number, minus 10, minus 20, it means it has negative impact. So it's like that. Weight. So it means that linear regression is we can associate the linear regression as this formula that we should select good parameters which will be sufficient or good enough that it will predict the y hat, the y. Okay, I think it makes sense. So we are saying that our task is to predict y from x by outputting this equation. So the performance is MSE. So MSE means that the difference between y hat and actual y squared and their mean value. Intuitively, one can say that this error measure decreases to 0 when y hat equal to y. Yes. We can also see that this thing 1 to m, 1 divided by m, and the length of this difference is equal to mse. So it means this thing, we can represent this as this as this equation. So it means norm. So there is two lines, it means norm. So, then there is also index 2. It means Euclidean distance, or L2 norm. You should understand it comes from linear algebra. If you don't know linear algebra, or if you need some recap, check my previous videos. And so what actually we want? So let's switch to my another screen. I will write and I will try to explain you. So let's switch to another screen. Okay, we have this screen. So I think, yeah, clear. Bismillah. So we are saying that we have task, and our task is to predict this y hat, which is equal to w, t, and x. So when we give this input value and we multiply this to w, we get this y. It does. So our linear regression computer system make a task, and it gives to us the y hat, this y hat. And now we need to measure its performance, how it is doing good or not. So we are using this MSE to measure the performance. So we are measuring performance by what? By subtracting, by finding difference between y hat and actual y, and we square it, and we get all sum of all this thing, and we divide by number of samples, number of rows, and we are getting this this p performance measurement. So what performance measurement? So we get some kind of number right here, some kind of number. So our goal is to get 0 here, which means that if y hat is equal to y, we will receive 0, right? If we say this one equal to this one, and if we find difference between them, it will be 0. And if it is 0, it means the computer system learned 100% the task, and it is doing very well according to the performance P. So our performance should be 0. So let me to write it here. So okay, so Bismillah. So here we want our performance MSE in the train to be 0, right? We say that if it is 0, it means our model, our computer system is doing very good at this task, so that our performance difference with actual experience is not different, and it means it's a computer program system is doing very well. So our goal is to make this MSE, mean square error, equal to 0. If there is no error, it means our computer system doing very well. So what we said MSE equal to. So we say this MSE we can represent is as 1 to m, and we will take a norm of this terrain minus y terrain n square. It is L2 norm, Euclidean norm. We call it Euclidean norm from linear algebra. So we want this equal to 0. So how we can represent this thing in other form? We can say this thing, for example, if L2 if of x, we can say it is this as this thing. So we will take as it is. So it will be, it will be as derivative of w will be equal to y terrain minus y terrain t to y hat terrain minus y terrain, and this thing will be equal to 0. How can we represent y hat? So we said y hat is weight t to x. So we will write it as that is. So it will be, look to the screen. So it will be derivative of weight equal to weight t to x minus y train, and there is t, and weight t to x minus y train equal to 0. Actually, I think let's for now I think we can say that let's for now omit this thing, omit, just say weight multiplied to x, open the squares brackets, so it will be y t to x t minus y train t to weight x minus y train equal to 0. So if I open it, it will be weight t to x t to weight to x minus weight to x to y train and t, and plus y train t and y train equal to 0. So we want that thing 0, okay? So in the end of this equation, we will come out with normal equation. So we will receive that thing. So now I think, now I think I missed one thing actually. Here so I multiply this thing to this thing to this. I didn't make this one to this one. So if I multiply this thing to this thing, it is the same as multiplying this thing to this thing, isn't it? So I can say -2 here because it's the same thing. So I am receiving that thing, this thing. Okay, now I will find derivative out of this thing. Here it will be so here you can see here's 2w. We have 2w, so that w square. So from that we will receive the constant 2, and we will receive the xt as it is and x as it is, and we will receive just only one weight. Then there will be -2. We have only one weight. It means it will be equal to 1. It will be, we will not write it, and it will be x, and it will be x x train. Yeah, it will be x train. It will be x train and y train, and it will be equal to 0. Why I write xt without x? So this one, I can write this one, you know, like here t and here t. Transpose, transpose. In that case, I will receive yt and y train as itself. And this one, we will not touch that one because it will be some kind of constant number. And now we receive this thing. So that's our final formula. So from here, we need to find this weight. So weight, okay. So weight will be equal to what? It will be equal to 2xt to y train divided by 2xt to x. 2 and 2 will go, and I can say weight is equal to xt to x minus 1 and xt to y train. So if we find this equation, we will find the weight. So this weight will be will result in measurement, performance measurement equal to 0. So in graphically, if we visualize it in 2D plot, for example, assume it is number of customers, price, revenue, assuming like revenue and price. So if number of customers is this much or this much or this much or this much, this much, this much or this much, this is data set, this is experience. And what we are doing now is that we are drawing a line which will perfectly fit, and the distance error between each row will be minimum, optimal. So in order to find this line, so we proved it that if we find this weight from this equation, then we can use this thing. I hope it makes sense. So to recap, so yeah, I think that's enough for today. So we talk about what's experience, what is task, what is performance, and we talk about what is learning algorithm, and we make an example with linear regression in theory, and I try to prove the normal equation. So this equation, we call it as normal equation. So that's it for today. Thank you very much, guys. See you in next videos.